Section 1 Introduction. In the world of reinforcement learning, RL, we've seen significant progress in areas where a clear reward function is readily available. These reward functions can be based on various factors, such as winning or losing a game, changes in game scores, or changes in the state of the game, like forward motion or the distance to a desired state. With the success of RL in these areas, there's been a growing interest in creating versatile agents that can handle a wide range of challenging goals in complex environments. However, one of the main hurdles in applying RL to these agents is the need for numerous reward functions for different goals. Creating a reward function that leads to the achievement of a specific goal can be difficult, time-consuming, and challenging to scale. This is true in both simulated environments, where it's hard to determine if an agent has achieved an abstract goal like building a house, and in the real world, where rewards have to be calculated from observations. To overcome these challenges, there's been a focus on automatically generating reward functions for training these versatile agents. One promising approach that has emerged recently is the use of vision language models, VLMs, to build reward functions in visual environments. VLMs, trained on large datasets of paired images and text, have shown to perform well on a variety of visual detection, classification, and question-answering tasks. They can also be fine-tuned for specialized tasks or datasets. Recent studies have shown that a pre-trained clip model, fine-tuned on paired Minecraft videos and text, can be used as an effective reward for training agents to achieve hunting and foraging tasks in Minecraft. Similarly, a pre-trained Flamingo VLM, fine-tuned on visual question-answering data, can produce an accurate visual success detector for a variety of natural language goals. Inspired by these successes, we explore the possibility of using off-the-shelf VLMs to derive accurate reward functions for language goals in visual environments. We propose a method of deriving a sparse binary reward for visual achievement of language goals from pre-trained clip image and language embeddings. We show how this can be used to train agents to achieve a variety of language goals in the Playhouse and Android NB visual environments. We believe that our work demonstrates how off-the-shelf VLMs can be used to train language agents without the need for fine-tuning on environment-specific data. Several previous works have explored using clip as a reward function for RL. The most closely related to our work is MineDojo, which first fine-tunes clip with Minecraft videos to form MineClip. MineClip is then used as a dense shaping reward function in addition to a ground truth binary reward function for programmatic tasks. The main differences between our work and MineDojo are that we use an off-the-shelf clip model, we do not use any ground truth information during RL training, and we train a single RL agent that can solve thousands of language-based goals. Other works have used VLMs for hindsight relabeling to do behavior cloning. For example, Flamingo has been used for hindsight relabeling and then behavior cloning in the Playhouse environment. Similarly, Dial uses clip fine-tuned on robotic demonstration and autonomous data that has been hindsight labeled by human annotators to further relabel a larger set of offline robotic trajectories, then also perform behavior cloning a language-conditioned policy. Finally, VLMs have also been used as success detectors. Success VQA fine-tunes smaller 3B Flamingo models to act as success detectors by formulating the problem as a visual question answering, VQA. Most of their experiments focus on how accurate the success detector is on offline datasets across various domains, with one experiment using the Success VQA model for reward-filtered behavior cloning. Section Summary. The use of reinforcement learning, RL, in complex tasks has been limited by the need for multiple reward functions. Vision language models, VLMs, have shown promise in automatically generating reward functions for RL agents. By leveraging pre-trained clip models, we demonstrate the feasibility of using off-the-shelf VLMs to train agents to achieve language goals in visual environments without the need for environment-specific fine-tuning. Section 3 Method. In this study, we're exploring how to use contrastive variational language models, VLMs, like CLIP to create text-based reward models. Our goal is to create a reward function that can determine whether a language-based goal has been achieved based on an image observation. This function will then provide a numerical reward. To do this, we build a reward model that includes an image encoder and a text encoder. The model takes in an observation and a goal, and then outputs a reward. If the goal has been achieved, the reward is 1, and if not, it's 0. We're working within a partially observed Markov decision process, POMDP, setting. Here, an agent observes, acts in an environment, observes the next observation based on the environment dynamics, and receives a reward with a discount factor between 0 and 1. In addition to the standard POMDP, our agent is given a language-based goal for the duration of the episode, and the reward is calculated using a VLM. The episode ends either when time runs out or when the goal has been achieved according to the intrinsic VLM reward function. We don't use the actual reward during training, only for evaluation. We first calculate the probability that the agent achieves the goal given by language description after acting in the environment, out of a set of potential goals. We do this by applying a softmax function with a certain temperature over the cosine similarity between the state's embedding and the language description's embedding across the set of potential goals. We then convert this reward function into a binary reward function by setting a threshold on the probability based on a certain hyperparameter value between 0 and 1. To avoid random rewards, we sample negatives uniformly from the task set and keep them constant throughout the RL training. In our experiments, the task set is a set of language goals that we know can be achieved in the environment. In our experiments, we're trying to answer these questions. 1. Does maximizing the VLM reward also maximize the actual reward? 2. How does changing the size of the VLM affect the performance of the VLM reward? 3. Can we predict the performance of an online agent from offline evaluation metrics? 4. How does prompt engineering affect the performance of the VLM reward? Our experimental setup is similar to standard online RL, where an agent maximizes returns through trial and error interactions with an environment. The only difference is that our agent trains against rewards given by a VLM instead of a ground truth or hand-engineered reward function. For evaluation, we plot both the VLM rewards, which we call intrinsic, and actual rewards, which are provided by access to the simulator. We train a policy that is conditioned on language and is initialized randomly, while the reward model is a pre-trained clip VLM with fixed weights. We use Muesli as the RL algorithm to optimize the policy against the VLM reward function. The environment samples a goal from the set of training goals, and the agent is tested on held-out goals during the evaluation. We use pre-trained clip models for all experiments. We investigate two types of encoder architectures for clip. The first uses normalizer-free networks, NFNets, which uses a ResNet image encoder with adaptive gradient clipping instead of batch normalization. The second is SWIN, which is a hierarchical vision transformer architecture for image encoding. We use the BERT architecture as the language encoder in all clip models. Section Summary. In this section, the authors propose a method to leverage contrastive VLMs like clip to create text-based reward models. They construct a reward model consisting of an image encoder and a text encoder, which takes in an image observation and a text-based goal and outputs a binary reward indicating goal achievement. The authors operate in a partial observed Markov decision process, POMDP, setting, where the agent receives rewards computed via VLM as a function of the observation and goal, and the episode terminates when the goal is achieved or a timeout occurs. Section 4.3 Environments and Tasks. In Section 4.3, we discuss the environments and tasks we used for our experiments. We used two visual environments, Playhouse and Android Envy. Playhouse is a virtual environment created with Unity, where the user has a first-person view inside a randomly generated house. We tested three types of tasks in this environment: find, lift, and pick and place. In the find task, the user has to locate a specific object and get as close to it as possible. The lift task requires the user to find an object, grab it, and lift it. The pick and place task involves finding a specific object, picking it up, and placing it near another specified object. Android Envy, on the other hand, is an open-source environment based on the Android operating system. It allows the user to interact with an emulated Android device in real time using touchscreen gestures. We conducted experiments with two sets of tasks in this environment. The first task, Open Common Apps, involves opening one of 10 commonly used apps like Gmail, Google Sheets, Chrome, Calculator, Clock, Messages, Phone, Google Calendar, and Google Docs. The second task, Open Diverse Apps, is an extension of the first task but includes 50 additional lesser-known apps. In Section 4.4.1, we discuss how maximizing learned rewards also maximizes the ground truth. We trained a language goal-conditioned agent to maximize the VLM reward without observing the ground truth reward. We found that the agent trained to maximize the reward also maximizes the ground truth reward. However, there is a systematic gap between the VLM reward and the ground truth reward due to the VLM reward's imperfect accuracy. In section 4.4.2, we explore the scaling behavior of the reward model as a function of the size of the underlying VLM. We evaluated the accuracy of the VLM reward against the ground truth binary reward on a fixed dataset of Playhouse trajectories. We found that increasing the size of the VLM used for the reward model improves the precision recall curves. We also found that the improved accuracy of the VLMs on offline datasets translates to better agent performance on ground truth evaluation metrics. In section 4.4.3, we discuss the impact of manually prompt engineering the text template on the ground truth performance of the agent policies trained on the VLM reward. We found that prompt engineering the text template for our VLM reward can significantly improve the ground truth performance. We hypothesized that using action verbs such as open in the prompt is not as helpful as providing a description of the successful states, such as screenshot of task, on Android.